So today we continue talking about second quantization and presenting our formalism, which we're going to use throughout the next few weeks. I want to remind you just a summary of what we did last week. We introduced a space of many-body states, which we call Fock space. And the system we have in mind is that we have some particles, some identical particles, that are either bosons or fermions. And these particles, their number can be arbitrary, and there is, in order to characterize the system, we concluded that we need to have only a few pieces of information. First of all, we have to introduce, or usually it's useful to introduce some quantum number which parameterizes the quantum states of single particles, okay? And it's just a basis. It's a basis that is that we can use in the standard quantum mechanics to characterize single particle states. And the choice of basis later on we'll see. Actually, I think today, towards the end of the lecture, we'll see that it's always possible to change basis if you want to have a representation that is more useful for a particular problem. Sometimes it's better to use a different basis, right? But we have a set of quantum numbers that we call lambda, okay? And these quantum numbers are coming with a set of spectrum, with a set of energy levels, which we call a spectrum. So for each lambda, there is epsilon lambda, and epsilon lambda is just the energy of a single particle if it's on the state lambda, okay? And the spectrum is useful to think about because it creates some kind of a hierarchy by which we can order the states, but it's completely arbitrary, okay? We don't have to go by the energies. We can order quantum numbers by position or by some kind of rule that we decide, but just to keep track, okay? Okay, so now the next thing that we have in our system is, this is something I think last week I didn't so much emphasize, there is a vacuum state. We assume that there is a vacuum state where the vacuum, which we denote it as 0, or sometimes you can call it vac or whatever, you can choose a name, but this vacuum is a state that is empty of the particles, okay? Now, you can say, okay, that's trivial. I mean, of course, there is always a vacuum, but a vacuum is not universally defined. It's just a reference state above which we imagine that we create our particles, okay? And I think I mentioned it last week that even what we call a vacuum of our universe is not empty of particles, in the sense that you can always create particles and create, the particle, antiparticle, and things like that. So the vacuum is a choice, okay? Later on in the course, we'll see that sometimes it's useful to redefine the vacuum. Okay, but once you have a vacuum, it's accepted that this is empty. And then we define a set of creation and annihilation operators, okay, which are corresponding to all possible lambdas. And I emphasize that the creation and annihilation operators are defined with respect to the vacuum. Okay, so choice of vacuum defines what is an annihilation operator compared to this vacuum. In other words, for every lambda, this is going to be 0. Okay? So, so there is an intimate relation between a choice of vacuum and the definition of creation and annihilation. Okay? If we choose a different definition of our vacuum, then what we call annihilation may turn into a creation. Okay? We'll see it in the future.
Why did you write lambda twice, the name in the sub?
So it's just a bad notation. I meant that these curly brackets just say that you know, lambda is running over. Never mind. Okay, you know what I mean. So it's just a notation that it's a set. It's a set of operators. Okay. And similarly for A. Okay, so this is important, okay? This is obeyed, there's some connection. A is an annihilation with respect to a given vacuum. Okay, and then our states are going to be, or the general basis of states are going to be of the form n lambda 1, n lambda 2, n lambda 3, etc., where n describes the occupation of the state lambda, and therefore in this notation the vacuum is just a state where everything is 0. Okay? So I'm claiming that in order to characterize a quantum state, a quantum any-body state with well-defined number of particles, the information you need is only how many are in each lambda. Okay? That defines it completely. With one more piece of information, we need to know the statistics, bosons or fermions, only 2 species to keep track of, and we are going to, throughout the course, parameterize them with an index zeta plus for bosons minus for fermions. Okay? Okay, so so this is the basis for doing a second quantization and defining a Fock space. And when I'm writing a state like this, so actually there is sorry. N1 is like n lambda 1. Okay, it's just a shortcut notation. So the set of all possible states of this form is a complete basis in terms of which you can write every wave function as a superposition. Okay. Great. So last time we also defined a creation operator, and I remind you of the definition. So how do you define generally an operator in any Hilbert space? You take an arbitrary basis state and see how the operator acts on it. And if there is a general rule, then it applies to, it really defines the operator completely. So when I'm applying this on a state with ni at place I, okay, and what it does is to leave all the occupations the same, except ni is increased by 1. But there's also a prefactor to the power half, and I soon remind you what is this index zeta, because it's different for bosons and fermions. And then we have zeta to the power si, n1, n2, n3, and ni plus 1 at the position I. Okay? This is, if you like, a definition for the creation operator. And the number s, which is called a string, is a sum over j starting from 1 to I minus 1 of nj. Okay, so it's a phase factor, or it's an integer that counts how many other particles are to the left of this index. Okay, that's why it's called a string. Notice that the sum goes until I minus 1. Okay, and the definition of it is kind of arbitrary up to an overall phase, but once you define it like this, you can keep track of what happens when you apply not one, but more creation operators one after another. And from this definition, we got two things. First of all, we found that, and I also remind you what is the definition of this ni plus 1 zeta is for zeta equals plus, it's just ni plus 1, so it's just itself. For zeta equals minus, it's ni plus 1 mod 2. Okay, so that if it's 2, it's 2 is 0. And that's how, for fermions, you can never get occupation of more than 1. Okay, so ni's can be only 0 or 1. Okay, that's the distinction. And from this, what we got is, if we take now, apply a dagger I, and after that a j dagger, and it's related to its to the exchange object by a factor of zeta. Okay, so this is an operator equation that we obtained, and I think you will prove it in your homework. Okay, well, I think the next number 2 or something like that, you will prove it just by plugging this and doing the algebra, which means that we can define a generalized definition of a commutator to be just, this is just the definition of this object, and we say that it's 0, okay? And if we want to write it explicitly, what is it for bosons or fermions? Then for bosons, which is zeta equals plus, we simply get a commutator, right? This is simply what we know as the commutator when zeta is 1. So you can write it like this. For fermions, zeta is -1, this becomes AI dagger, AJ dagger plus AJ dagger, AI dagger, which is an anti-commutator. And this is the notation that is usually used. Okay. So, so we have an operator that adds particles, and it obeys this algebra. Okay? And we were able to show also that this is obeyed for any I and j. Okay, so I can be equal to j, I can be different from j, it's always 0. Okay? Great, so this is an important thing to note. A side thing that we noticed is for fermions, for zeta equals minus, the square of any creation operator is identically 0. Okay? And that's enforced by this mode 2 thing. Okay? So if you try to create another particle, you get 0. Okay? Excellent. Okay, so this is the thing, and then now the last thing that we got from this is that A dagger in particularly creates a single particle when it acts on the vacuum, right? So you can start from a vacuum, which is the empty state, and apply A dagger once and again for each lambda, and that's how you get these states. So the state that we wrote as a sequence of occupations, these Fock states can be expressed as a product over all the lambdas of some normalization factor, which is the square root 1 over square root of the n factorial of A lambda dagger to the power n lambda. All that acting on the vacuum. Okay, so this is a closed expression for a Fock state. Okay? You can express it in terms of the vacuum and the creation of matters. Okay. Good. Okay, so we have a creation operator. It obeys some algebra rule. Now what we are missing to complete the description is the Hermitian conjugate of A dagger is the annihilation operator. Okay, and in fact that's an assumption that now we'll prove. Okay, so now I'm going to show you, once we defined A dagger like this, we can deduce what will be the annihilation operator. Okay, we no longer have freedom to define anything, because this, once we define it like this, everything follows. Now I should stress one thing. Well, how do we know that A dagger is not Hermitian? It's not a Hermitian operator. How do we know that?
Conjugate and flip the sign.
A on the vacuum is 0.
First of all, yeah. Okay, that's easy to see. You can also see that it cannot have an expectation value. If you take any basis, any Fock state, and try to compute the expectation value of a dagger, you always get 0. Why? Because you have sandwich something that has not the same number of particles, right? So this is something important that I want to stress. All the states with different ends, even if only one of the ends is different, are orthogonal. Okay, it's an orthonormal basis. So we have this rule that if I take one Fock state and I calculate the inner product with some n prime and 2 prime and 3 prime, this inner product equals a delta of n1 prime, a delta of n2 and 2 prime, just a product of many delta functions. Okay? This is trivial, it's just orthogonality. Okay? And therefore a dagger doesn't have any finite expectation value in any Fock state, and therefore it does not have an expectation value, and therefore it cannot be a Hermitian operator. Okay? Okay, so now let's see what is the annihilation. Okay, so this I can erase. I'm leaving the string here. Okay, and let's keep this in mind, but I don't need to write it explicitly. And now what I'm doing, let's take the original definition of a dagger. We have here an equality between this state and this state. And we can always look at its Hermitian conjugate. And the Hermitian conjugate of the left-hand side, okay, so let's do Hermitian conjugate. What it will be. So the Hermitian conjugate of a substate alpha is this, right? So this is in general. So here, the Hermitian conjugate of the left-hand side is, you turn it from a cat to a bra, so it's n1, n2, n3 looking like this. And AI dagger turns into AI, right? Okay. What is the right-hand side? The conjugate of the right-hand side is simply this number, this factor, times the bra version of this state. Okay, so I'm not even writing it. Now, why is the conjugate of this number is itself? Why is that? Because it's a real number, right? Everything here is real. Zeta to the s is -1 to an integer power, so it's either minus or plus 1. And this is also a number, a real number, okay? Okay, very good. So why am I mentioning it? Because, so from this we cannot deduce what is going to be AI acting on the right, right? We cannot deduce. This is just an identity, if you like, right? If this is a state, this is its conjugate. But what I'm hinting is that you can look at a matrix element of the operator that we want to learn about and interpret it in two ways. One is when AI acts on the right or when it acts on the left. Okay, so I'm going to look at the following matrix element. I'm going to look at a matrix element of A dagger between two Fock states, two arbitrary Fock states. Okay? Let's denote the state on the left. We are going to denote it as without the prime. Okay? And this one is n1 prime, n2 prime. Okay? Right? Okay, so there, sorry. This is, okay, but I want to be, because AI dagger acts only on the position I want to include somewhere in the ith state, here I have Ni, okay, and here I have Ni prime, okay? And actually all the others, I don't really care what they are because AI dagger does not act on them. Now, just from the definition, I know how to calculate this matrix element, right? Let's calculate it. So what I have to do is to look at, so we can view it as an inner product between two states. One is this, the one with without the primes, and this guy we are going to replace by the right-hand side of the equation. So it's giving me Ni plus 1 zeta to the power half times zeta to the Si times the state which has all the occupations the same as before, but Ni prime turns into Ni prime plus 1. Correct? Right? And now this is just a number which I can take outside times an inner product of this state with this state, right? And it is just a product of deltas. So let's write it down. First of all, I have this.
Shouldn't it be n tag in the first brackets? And
Sorry?
tag I plus 1 to the power of half?
Yes, sorry, you're right, completely right. Thank you. Yes, it's Ni prime. Okay? It's just I copied the definition, but everything here is with the prime, including this. Actually, this is also, okay, to be more careful. Sorry, thank you. Okay? So, what I got is Ni prime plus 1 times zeta to the Si prime times a product of deltas. So, all the deltas are N1, N1 prime, N2, N2 prime, but there's one delta that is different because Exactly, so I have to, so it's a delta of ni with ni prime plus 1, right? Okay? Okay, very good. Now let's take this matrix element, which is generally some complex number, and calculate its complex conjugate. Okay? What is the complex conjugate of this? Now I'm doing complex conjugate. So I'm putting a star on everything because a matrix element is a number, just a number, right? What is it? It's given by, I have to reverse the order of the prime and the not prime, and I get ni prime. This A dagger turns into A, and then I have N1, N2, Ni. Okay. So this is nothing but a complex conjugate of the top row, left-hand side. But then the right-hand side has also to be complex conjugate, right? But the right-hand side is a real number, right? So it's just itself. Let's write it down explicitly. Zeta to the Si prime times the product of the deltas that I copied from here, where in particular the delta connects or equates, sorry, Ni to Ni prime plus 1, right? Okay. And now what I'm going now to give you an alternative interpretation of the left-hand side of the equation. I got it from conjugating the matrix element of A dagger. But you can also think of it as a matrix element of A between this state and this state. Well, now the prime and not prime have been interchanged. Okay? So let's look at it like this. And now I want to view it as an inner product between the state with the prime to the state where AI acts on this, and I want to rewrite this cat state as in the form of just a Fock state. And in fact, I know how to write it. Why? Because notice, so first of all, there is here a number that is just there and I have to keep track of it. But apart from this prefactor, what I have is a product of delta functions. The product of delta functions is the inner product of two Fock states, right? What is the state? So let me just copy first. I copy the prefactor. Let's do that first. So the prefactor is Ni prime plus 1, but Ni prime plus 1 is Ni, because this is enforced by this delta. Okay? So instead of writing it as Ni prime plus 1, let's write it as, that was my eraser. Let's just write it as Ni zeta to the power 1/2. Okay, sorry. Okay, and now Si prime, I claim that Si prime is equal to Si. Why? What is the definition of Si? It's the sum of all the occupations up to I, right? But all the occupations are the same, only I changed by 1. Therefore, actually, Si prime equals Si, so I can just write it as zeta to the Si. Okay, that's the prefactor, expressed in terms of the Ni and not Ni prime. And now I'm left with, apart from this, this number, I have deltas, which I interpret as an overlap of this state with something. What is this something? Which will give me an equality. It must be something where all the occupations are the same, right? Because these are the deltas, except at the place I have not Ni, but Ni minus 1, right? Because the left, it has to give me a delta with Ni prime. Okay? Here, because this is like, I can rewrite it as a delta of Ni minus 1, Ni prime, right? It's just, yeah, this is an identity. So here I have Ni minus 1. Okay? So you see, what did I get here? An equation just like the one on the top, which dictates what does the annihilation operator do, and we see that indeed it's an annihilation operator because it acts on a state with occupation Ni and reduces it by 1. And it gives me some prefactor, which is a normalization. Okay? That's what it does. Okay, so let me copy the result. Is it clear? Okay, just logical steps. So, sorry. If you have a question, this is the time to ask before I erase everything. What will... So let me repeat again the calculation. What I did is, first of all, I took an arbitrary matrix element of the operator AI dagger, which we already introduced. Okay? And we wrote an equation for it. Then we complex conjugated it. We use the fact that the right-hand side is actually a real number, and therefore this conjugation just gives you, okay, it gives me the same number, but you can also rewrite, when we do the conjugate of this matrix element, we get a sandwich of AI between two states. Okay? And now what I did is, this is the crucial step. I looked at the right-hand side as some number times a product of delta functions. The product of delta function I interpret as an overlap, as an inner product of two Fock states with the corresponding operator and occupations that obey these deltas. Okay? So this is how I got it, and now let me copy it to the top, because now we have an identity, an operator equation.
Sorry, what's the definition of SI below?
SI?
The below SI is C, and
Sorry?
AI. Yeah, this.
This is the same.
They are same because one is AI, another is AI dagger. So
it's not dagger. First of all, it was prime. SI is a real number.
Yeah, I mean this comes from AI dagger, right? AI dagger times the state, and below is AI times the state.
Because you have to cancel out, you multiply the -1 time to the SI.
I'm not sure I understand. So this here I just, this to get this right-hand side, I use this definition. Okay? Now there was another step I took, which is to realize that because of the delta function, the deltas, sorry, not delta chronicles, Si prime is equal to Si. Okay? So it's because, you're right, it's not, so Si prime is just putting a prime here. But the deltas enforce them to be equal. Okay? Therefore, it's the same string, the same factor. So let me erase it and rewrite the result is that AI acting on an arbitrary Fock state with position I occupied by Ni. This I think I can erase, but remember what it is equal to Ni zeta to the power Si times state with Ni minus 1 at the position I. Okay? And now we have, actually, if you like, this equation that was the definition. The second equation was derived, but together they define the operators, right? And in particular, it's easy to verify from here that AI acting on the vacuum will give me 0, right? For both bosons and fermions. That's it, okay? Very good. So, so now that I have a well-defined basis for my Hilbert space, which is Fock state, I have a well-defined definition of the two sets of operators. I'm claiming that any physical operator can be expressed in terms of combinations of A and A dagger. You don't need anything else. Okay? It's a complete description, and what you need to know in order to work with it, because we also saw that the states can be expressed, and let me rewrite it again here. The definition of, not definition, but there is an identity for the Fock state. The general Fock state can be expressed as a product over all i's or all lambdas, if you want to be use a general definition of the quantum number of A lambda to the power n lambda acting on the vacuum. Okay? Sorry, of course, David. Okay? Right, so you can see that if I want to, you see where I'm heading. I'm claiming that any physical operator, the energy, the momentum, the position, the density of particles, whatever, it can be represented as some combinations of A's and A daggers. And then if you want to do calculation with it, you need to know how to compute the matrix element of each operator, right? And then maybe diagonalize the problem if you're lucky and you can do that, and so on. But you already realize what is the tool that I need in order to work with it. Because generally speaking, if I take two a matrix element between two arbitrary Fock states. Each of them has this form with some product of A dagger. The Hermitian conjugate will be a product of A's. And in between, I have some combination of A and A dagger. And what you also know is that AI annihilates, or for any I or for any lambda, it annihilates the vacuum. So in order to get eventually just a number, what you need to be able to do is to somehow shift all the annihilation operators to the right and act on the vacuum, and if then you get, we'll see later how we do calculations, but there is some information you need to know in order to do calculation, and this is what happens if you exchange two operators. And for that you need to complete the algebra. So we already derived, we already found that for bosons and fermions, okay, or equivalently zeta equals plus or minus, the daggers obey that their commutator is 0 for any I and j, and for fermions it's the anti-commutators. And we got it only for the dagger operator because this was what we defined last week. But now we have already an identity for the annihilation operator. So we can also check, first of all, okay, there is something that trivially already follows from this. If you look at the commutators or anti-commutators, the right-hand side is 0. So if you do Hermitian conjugate of the left-hand side, it will also be 0, right? What is the Hermitian conjugate of the left-hand side?
A.
It's A, right? So therefore, from this it follows, and this is true for any ij, right? So from this, it trivially follows that the same commutators will hold for the annihilation operators. And it's the same for fermions and bosons, except for fermions you get anti-commutators. What I'm still missing is one piece of the puzzle, and that will complete the algebra. What happens if I apply A dagger and then A? Or I apply first A and then A dagger. Okay? To do this, you need to take these two equations and just do the algebra. Okay? And you'll do it in your homework as well, I hope. And you're going to find, and this is already results of our work, if you do it correctly, that for, and again I'm distinguishing bosons, fermions, which are according to this zeta, AI, AJ dagger. Now this commutator is not going to be 0 in general. It's going to be a delta of I and j. Okay? And for bosons we already saw it, right? This is just the usual phonons or photon operators. This we already know, except, yeah, we have a delta. So if I is different from j, they are commuting with each other. It doesn't matter if it's A or A. But we see that for the same price, we get the same thing for fermions. Okay? Just using this factor of zeta everywhere correctly. So if you look at this anti-commutator, which if to write it, just to remind you what it means, anti-commutator, it's AI, AJ dagger plus AJ dagger AI, and you see because of the plus, it doesn't matter if you put the dagger here or here, but okay, but this also gives a delta. Okay? Very simple. And this is it. We have a set of algebra rules for the elementary, all the building blocks, okay? A dagger, A dagger, right? And what will be the commutator of A dagger A with the same indices? Right? And for the anti-commutators, it's the same. Okay? Okay, so from this you basically have all the combinations you need. But then you can also ask, okay, what if I have, what will be the commutator or anti-commutator of A and AI and A dagger square? Okay? You can do the algebra, and to do that, actually, you need some formulas. So you'll do it in the tutorial and also in your homework. But there are some formulas that relate when you have, for example, just to give you an example of kind of tools you need. Suppose I have 3 operators, A, B, C, and I have to calculate the commutator of A and the product of B and C. This can be reduced to a sum of contributions. I'm not writing the formula here. Actually, here the formula is simple, but I'm not writing it, but you can write it as a sum of 2 things that involve only commutator of 2. Okay, so in fact you can calculate there are a lot of formula that you can use that are just making use of these elementary definitions, elementary algebra rules. Okay? And that's it. These are the Lego blocks from which we are going to build towers. Okay? Or machines or whatever. All right, very good. So we are going to see a lot of examples, and in a few weeks you're going to be experts in using it to do calculations. Before we go on to some more complicated things, let me mention one important thing, that all of these basic definitions, the basic definition of the creation and annihilation operators assume that you take some basis for your single particle states, and I call it lambda, but it's usually thought of as some quantum number that is useful to describe the system. Now, what will be this quantum number? If you're talking about a system that has a translation invariance in space, usually the good quantum number is the momentum, k, right? The wave vector. If you're talking about spin that is in the z direction, what is the good quantum number? Sz, okay? Up and down, etc. But sometimes you discover that you chose a basis, okay? According to the basis, I defined A lambda and A lambda dagger. Now I have to change basis. Why? Because I discovered that there is some symmetry in my problem and there is a more convenient basis. I want to change from one basis to another. We do it all the time, also in elementary quantum mechanics, right? We go from real space to Fourier space, or from Sz to Sx, right? So I want a general rule of how to change basis. And by change of basis, I mean, let's not confuse two things. I have a basis, a complete basis, if you like, for single particle states. This is what I denote as lambda. Okay, so lambda are single particle states. Okay. The other basis, the Fock basis, is the states of occupations, that is defined by occupations of many particles. That's a basis for the many particle Fock space, but it's usually you pick some basis for the single particle to set up the definition. Okay? But now sometimes you need to change basis. What do you do? Let's see that we can do it in a very simple way by using the change of basis that we are already familiar with for single particle states, right? For single particle states, we know how to change from basis lambda to some basis, let's call it lambda twiddle. How do we do it? Let me remind you. So, suppose I want to change, I have my set of states in lambda, and I know that any state in this Hilbert space of a single particle state can be expressed as a superposition of lambdas, right? So now I want to switch to another set. Lambda twiddle is another set of states. It's not different numbers for the lambdas, okay? It's some different index. Okay, like real space and Fourier space. Okay, so I know how to convert it to a representation in the lambda basis by using what we call resolution of identity. Remember it from your undergraduate? I don't know if you remember, but let me remind you, just to be on the same page. Or shall I write it somewhere? Let's write it here. Okay, so there are a lot of ways to write it, but usually the resolution of identity is a sum over a complete. So you have a set of states, alpha. Okay, now it doesn't matter if it's single particle, many body, or whatever. It's a complete set of states. You can write the identity operator as a summation of all the projectors onto the states alpha. Okay? If you convert it to a matrix form in the basis alpha, it will be a matrix that has 1 on the diagonal and 0 everywhere else. Okay? So this is called the resolution of identity. And there is a very nice trick that you use, I believe, in your undergraduate studies as well, that because it's an identity, you can always plug it in anywhere you want because it's just 1, right? So let's take this state lambda twiddle and plug in the resolution of identity here, but here I'm writing it as a resolution of identity in the basis lambda. And this is what I got, okay? So what I wrote is tautology because this is 1, right?
That works for any set of
for
states.
any state, any set of
not
states.
Not specifically for single particle.
Of course, but here it will be useful to do it for single particle states because then otherwise you're comparing apples and oranges and you don't, because here in this case, okay, so what you got here, there are two they belong to the same species. Okay, there are two alternative choices for a complete basis for the states of single particle. But now let's just rewrite what we wrote here in the following way. We notice that the inner product of lambda and lambda twiddle is just a number, right? Because it's just a number, I can put it here, right? It's just a coefficient, it's some number, generally a complex number. So I can reorder it and write it as a sum over lambda of this thing, this matrix, this inner product times lambda. Okay? And what I wrote here, if you want, you can call it C lambda lambda twiddle. It's some complex number, right? Okay. So this is something you've seen already, long time ago. But now I want to relate it to second quantization, because what I really want is to be able to convert from a set of A lambda daggers and A lambdas to A lambda twiddle dagger. But this allows me to do it. Why? Because what is a single particle state? How do you write a single particle state in second quantization? You take the vacuum and apply the A lambda dagger once, right? So this is an identity. Okay? And similarly, lambda twiddle, it's true for any basis, and therefore I can also write A lambda twiddle as some creation operator acting on the vacuum in my new basis. Now let's plug it into the expression that we got. On the left-hand side, I have A lambda dagger twiddle acting on the vacuum. On the right, I only have to plug it in here, because this is already a number, okay? So I leave it as it is. It's a number, it's not an operator. So you can easily convince yourself that we get the following identity: A lambda twiddle, A lambda twiddle dagger acting on the vacuum, this is the left-hand side here, is given by a sum over lambda of lambda lambda twiddle, A lambda dagger acting on the vacuum. Okay? Okay, so therefore what it means is that what I have on the right-hand side, what is it? This thing is just a different way of rewriting A lambda twiddle dagger, right? And in fact, if you want to be more careful, you can also show that these two operators are identical when they apply on any. You can just show it iteratively. They are the same if you act on any Foster. Okay? So as a result, we get an operator identity. So A lambda twiddle is a sum over lambda, lambda twiddle, A lambda Okay, this is now, it's an operator identity. You can write this operator as a superposition, not a superposition, a sum of the A lambda daggers with some coefficients. And these coefficients are some numbers, okay? So it's just a linear algebra conversion to a new basis. And now you can also apply a complex, apply a Hermitian conjugate on the two sides of this equation, right? So if this is true, let me put it in a box, then it's Hermitian conjugate also obeys the identity, so it's A lambda twiddle, the annulation operator of lambda twiddle is given by a sum over lambda. Now, be careful, this is a complex number, so I have to switch exactly, I have to switch the two, or equivalently just say this is the same coefficient complex conjugate, right? It's the same thing, times A lambda. Okay, so the second equation is an identity for the annulation operator. Okay, and this is general. It's a transformation of basis for an arbitrary choice of two bases. Okay, let us take a concrete example. Suppose I have what I call the lambda twiddle is just R, real space, position in space. Okay? Okay, so this will be an example. Coordinate in space. Okay? So now there is one thing that we want maybe to be a little careful about. Yeah? What?
No, maybe it's something you're going to say just kind of will, because the operation of the letter operators is discrete, like from one state to another state, or from a specific number of particles to another particle. But here you take it to position, and position is not a discrete parameter.
Exactly. That was exactly what I was.
Sorry.
Yes, you're right. So here there is a bit of a jump, which is that our definition of a basis was kind of defining a discrete set of states, and position is continuous variable. But we already know, we're already used to the fact that we saw many times that any continuum is nothing but the limit of a discrete thing when you take the division to the limit that, to the continuum limit, right? So any continuous variable can be thought of a case where you have cells, and you take the limit that the cells are tinier and tinier and get infinitesimal. But then what you're going to find is that if you want to properly define a creation operator for a particle at a point R, it's actually meaningless because it's a measure zero, right? So what you're actually defining is something that has units, because it's something that if you convert it to the probability, so you already know it again from your undergraduate quantum mechanics, there's no meaning of saying what is the probability to find the particle in some state when you have a wave function. It's the absolute value squared, right? If you're asking the question, what is the probability to find the particle exactly at point R? The answer is mathematically zero. So what you're actually talking about is not probability, but probability density, right? So here we do the same. Instead of defining A dagger and A of R, with like an index, we define field operators, which, also in the literature you denote them by psi and not by A, okay? So psi dagger of R is going to be something that describes up to some normalization factor that has units, and we'll shortly discuss what are the units. This creates a particle at a point R, but only in the limit where you take some surrounding of this point, if you like to be careful, okay? So, but this is actually just taking exactly the same definition that we had here. So you can write it, express it as the overlap of lambda with lambda twiddle, which is now R. We shortly will remind ourselves what is this, times A dagger of lambda. Okay, so here I just applied this formula, and I write this definition, just copying from here, but I just give this operator a different name. Okay, I don't call it A, I call it psi. But why do I have a different name? Because let us understand. Okay, let me actually, maybe it will be easier to do it on the annihilation operator. So similarly, I can define a psi without the dagger to be annihilation of a particle at position R, and it is again given by this formula, but now it is R lambda times A lambda. Okay? Now, let us remind ourselves, what is this? So in fact, it's a number, okay? It takes complex numbers, but what is it? It's actually the inner product of a state lambda with a state R. What is a state R? It's a state, it's a delta function in space. Okay, it's a state that is localized at the point R, and you know that it's actually a delta Dirac, right? So it has units, non-trivial units. And it is nothing but what we called in undergraduate quantum mechanics phi lambda of R. Okay, the wave function. It's the wave function, okay, in the real space representation. Okay, so when you convert from a Bryant-Ket notation to wave functions in space, like what you plug in the Schrödinger equation, this is the way. Okay. So, for example, if lambda is k vector, right? What will be this? Just up some normalization factor times e to the I k dot r, for example, right? But lambda can be anything else. It can be a harmonic oscillator state, and then it's some wave function. But it's a wave function, and therefore it's describes a distribution. And it has units. What are the units of a wave function? If you square it, if you take the absolute value square of a wave function, you get a probability density. Okay. What are the units of probability density? It's 1 over volume, right? So the units of these are 1 over square root of the volume. 1 over square root of vectors, okay? and therefore psi and psi daggers are not pure numbers, they have non-trivial units. Okay? So this is how we keep track of the continuous variable, and therefore, and now going back to the first equation, which is just a Hermitian conjugate of the first, what is the coefficient here? So if this is phi lambda of R, it's a function of R, and it's a complex function in general, this is phi star, right? Right? Okay, so these are the formulas how to convert from any basis to real space. Okay? But yes?
Practically speaking, it will be an infinite summation then.
Of course, yes.
Okay, so
Of course. Let's take an example. And then, okay, when I wrote it like this, I start from a basis lambda and convert to R. But I always have the inverse. There is the inverse transform, if you like. How it will look. So actually, the way I wrote it here, you just put the twiddle on the other guy and you get, so it's easy to see how to convert. But when you have one discrete variable and one continuous, the inverse transform, you have to be careful because the sum over R is actually an integral. Okay, so the conversion is, so the inverse transformation is that, let me just copy it to here, that A lambda A lambda dagger is going to be an integral over space, okay, I'm allowing d-dimensional space of, now you have to be a little more careful because it's going to be now f lambda of R psi dagger R. Okay, now why I have here phi lambda and not phi star? Because it's the inverse, yeah, you have to do the inverse transformation and then it gives you the Hermitian conjugate, the complex conjugate, sorry, of the coefficient. And similarly, A lambda is going to be an integral over R of phi lambda star R psi. Okay? Let's take an example, which I already mentioned before. Wave vector, okay? Fourier. So just Fourier transform. Okay, so the lambda, erase this, I don't need it anymore. So let's take lambda to be the wave vector k. And let me first apply the general formula here. I get that I can represent the creation operator field psi dagger R. I can represent it as a sum over k of the coefficients are now going to be the functions phi k of R, but phi k, write it straight away, phi k of R is 1 over 2 pi, or it doesn't matter, it's some convention for the normalization, e to the I k dot R, right? Remember that? Free particle. wave function. So this is what you plug in here. It's actually, let's forget about the 2 pi because it's a matter of definition, if you permit me. Okay. Just e to the I k dot r. Okay, let's actually keep it, because sometimes it's useful to cancel the integral or whatever. And then I have my a dagger k. Okay, and here notice that, by the way, that here I assume that the k vectors are this discrete set, which is true if you have finite boundary. But once again, if we take it to infinity, k as well is going to be a continuous variable, and there's no problem with that. Okay, okay, and the sum will go to an integral. All that we already know how to handle. Similarly, psi of r can be expressed as sum over k e to the minus I. Sorry. Just I wasn't careful, because for the dagger you have phi star. Okay, it has to be phi star. So here I have a minus. Okay, and here I have e to the plus I kr. What I wrote here is nothing but a Fourier representation for the real space too. Okay? Just like for functions, we can also do it for operators, that's all. No difference. And the inverse is of that is that we can express ak dagger as an integral dr e to the I k dot r of psi dagger r, and ak is its Hermitian conjugate, which is an integral e to the minus I k dot r psi. Okay, so either way is good. Now there is a reason why I'm specifically interested in the real space, because as we'll see soon in the next lectures, one of the important operators, physical operators, that I can imagine working with and looking for its matrix elements and so on, is the density of particles, right? And the density of particles is defined in real space, okay? But many times the real space is not a good description for the Hamiltonian, because the Hamiltonian is better described in momentum space. So it allows you to make the conversion, okay? And vice versa. Okay, so this is how you change basis. So we have actually all the machinery, all the tools to go on. And let me summarize. We learned, first of all, that we have here a new language where we can define many-body states in Fock space. Fock space is a state of states, many-body states that are defined by occupations of some quantum numbers, some single particle states, and by the statistics, bosons of fermions, and the statistics, all of it is embedded in the algebra of the operators. Okay, so for both species of particles, you can define annihilation and creation with respect to a given vacuum, and you can, and then we have a complete basis for the states. What we need now in order to describe physical Hamiltonians, physical systems, is how to write operators. Any physical operator, like, as I said, energy, density, momentum, interaction, okay? Something that is called, something that describes hopping processes from site to site. All of this we want to be able to write with the same building blocks. We already know how to write the wave function. Any wave function, any many-body state, can be expressed as a superposition of Fock states. And each Fock state can be expressed as a product of A daggers acting on the vacuum. So we have a complete description for the states. We now want to write expressions for the operators that are in the same language. And then we'll be able to calculate, just using these algebra rules, we'll be able to calculate matrix elements, expectation values, to solve the problem, essentially, okay? And essentially, just like in any elementary quantum mechanics problem, what is our ultimate goal? We have a Hamiltonian that describes the system of many particles. We want to find its ground state, we want to find its excited state, we want to find the energies. In other words, we want to diagonalize it, okay? And it's a challenge, but at least we have a tool how to describe it. So, so let me just start towards how to write operators, and we'll continue with that next week. As I said, all the operators can be written, and that's our aim at this point. I want to write any operator you give me. I tell you how to write it in second quantization. And then we're all set. Okay, so before we do that, we need to classify the types of operators you can have, okay? So in a single body operator, problem, the operators you have are, okay, now it depends on what kind of Hilbert space you're working with, but if it's real space, you can write, or something that is described by Schrödinger equation, you have kinetic energy and potential energy, right? And you have coordinate and momentum. If you have a discrete space like spin, you have sigma x, sigma z, and various any operator can be written as in Pauli matrices, okay? Now, and there is a classification of the types of operators. In a Fock space of many body, you can classify the operators by how many particles are involved, okay? And the first and simplest type we're going to discuss are one-body operators. Examples. So what is a one-body operator? It's an operator that acts only on one particle, although your system has many particles. But it acts on each particle at a time, okay? It doesn't involve interactions. So in fact, any problem where you have, if your Hamiltonian describes particles that are non-interactive, that are independent, then it contains only one-body operators, right? Because what is a one-body operator? we're going to eventually relate it to a sum over some operators, each of which acts only on one particle. An example for that is just the total kinetic energy. Okay? What is the total kinetic energy? Just the sum of kinetic energies of the particles, right? Just like in the first lecture, we discussed the masses on the spring. The kinetic energy only involved the two particles, but so in general, let us denote a one-body operator. I denote with an index 1, okay? If I write it in first quantization is the language where I keep track of the particles. I have capital N particles. I can write it as a sum over n of, let me call it little o n, where o n acts on n is a particle index. Okay? That's how you write it in first quantization. In second quantization, this will not be a useful notation because you have identical particles. Remember, we are talking about systems of identical particles. Okay? So you don't care about the index of the particle. You care about how many of them occupy the state lambda, right? So you want to rewrite it in terms of A's and A daggers of the corresponding quantum number. And then, but just an example for that is the kinetic energy, right? Kinetic energy is in first quantization, you just write it as for example. But I can think of other kind of when I write it like this, notice that of course you know how to write the kinetic energy in the more convenient basis, which is the states of wave vectors, right? So what is it going to be? It's just going to be, so everything can be written as a summation of k of something, okay? And what you need to know is how many particles are in a state k. But you can also discuss single body operators that are taking one particle. So you can imagine an operator, and that's an operator that has well-defined matrix elements that describes a hopping process of a particle from site I to site J, like in tight binding model in solid state. If you remember, right? You have some discrete lattice sites, and you can have a process, a term in your Hamiltonian, that describes the amplitude for jumping from state, or tunneling, if you like, from site I to site J. This is also a single body operator. Why? Because it involves only one particle. It moves it from A to B. Okay? So we are going to show next week that most generally one-body operators will always involve just a product of two A's and A degrees. Okay? But we'll show it next week. And, we're running out of time. And then at 6 o'clock, Sarah will continue.
Thank you.
So, today we will mostly gonna go through the basic definition of second quantization, how we do notations in quantization, the very basic operators with whom we'll build everything else. in the future. In short, second quantization is a very simple way to it's a method to express a very complicated system in a very simple way, or basically I like to call it cheating, because I'm a physicist and I love to do some cheating. Let's say, for example, that I have some sort of quantum property, let's call it lambda, which can be any number from the very known set lambda I. In the past, you might have said I have a particle that has lambda I as its lambda quantity, lambda I, and it has some sort of wave equation, A times E I lambda I t, for example. I'm just writing nonsense. It doesn't have to mean anything, right? And then maybe, like, I don't remember if it's quantum 1 or quantum 2, you learned this first quantization. You learned that instead of writing the entire wave equation, you can just write lambda I and say, okay, I have a particle lambda I, and I can do some, maybe I can do some operation to move it to a different lambda using some, I don't know, some operation A. So what if I have, instead of one particle, I have so many particles, all with quantum quantity lambda I. Let's say I can't even distinguish between them. What am I supposed to do? Would I write a million different wave equations? Would I write a million different brackets? No, the basic thoughts behind second quantization is to take this entire complex system and write it simply as a state that just counts how many particles or electrons, whatever, how many particles have phonons with energy or quantum number Ni, right? So this is basically just a super simple way to write the grand canonical version of this, of everything that you did in quantum 1 and quantum 2. I'm just doing a lot of shortcuts and not writing the entire complex thing. Okay, so what I did is basically just put them all in a box. And then I can have another box with lambda j and so on. It will look like, in the most general form, 1, 2, 3, and so just to make sure everyone understands this, let's say I have 2 particles with energy 1, 5 particles with energy 2, and 7 particles with energy 3. How would this state look like? I would, let's call it size. What do I write? 2, 5, 7. Yeah, 2, 5, 7. I can write all the zeros, but usually we can just simplify it. Simplify it by closing this this bracket. This is a cat. If you want to be clear to other physicists who will later review your work, you might also put indices here. But again, this is something that you can neglect if you remember or if you're consistent with your writing. So all of this is just a way to simplify things. Right. Actually, I'm not going to make research yet. Now, we also know that quantum is very funny with probabilities. I can have a state that either has, let's say I have a box, that either has a particle in it, doesn't have a particle in it. Well, just like you saw probably in the previous quantum courses, this one I can just write as a superposition of nothing, 0, when there's no particle, and 1, there is a particle. Square root of 2 for statistics, for probability and normalization. So the absolute general term, I'm just going to move this a little bit. We'll have a sum here over all the possible cases. You saw this notation for a summation before? Okay. See. This is the most general state in the second quantization, and in fact, every state that you'll see in the course or that you see in your work can be written like this. We call this the Fock state or the number occupation state. Just a name that you should remember. Right. And when I say every state, I mean every state. For example, laser state, when you don't know how many photons you actually have, it's this one. When we later talk about superconductivity, we can simplify this state as well, so on and so forth. Basically, what I'm trying to say is that you can spread the entire quantum space function space.
It's not the number of the coefficients are not necessarily the same number as the particle, as the number of states.
Really? Yeah. Okay. Yeah. When I say particle, it might be a bit misleading. I'm just used to saying particles, but the more general term would be phonons, and then you can actually count them.
What I meant is that, for example, given that I have a state, it doesn't have to be a superposition of all ni. When you write it like that, it means that you have a coefficient for ni, a coefficient for n1, 2, 3, 4.
This C, C absolute value squared equals the probability to get this line. That's what you asked.
So
it's a superposition of many different states. This is the most general state, the most general quantum state. And you can represent every other state that you encounter using this. Okay, so I told you how to represent stuff, but that's not enough. I want to add photons or phonons or remove phonons. So for that we need to talk about creating particles and destroying them. And we'll start by a very important definition in every mathematical part of physics, the vacuum state. 0. Now, I'm going to define an operator without really going into depth about all of its properties right now. We might do it later in the course. I'll call it the creation operator. AI dagger. If I'll take the vacuum state and apply a creation operator on it, position I, I'm going to have to count up to the I spot, so all of this I minus 1. For now, this is a magical operator to just put a phonon where I want. What if I want to do it again? So now, my dagger, this. want to add another phone. Well, that's simple. I just go again to the I spot and put another phone in there. And there will be some normalization factor, square root of 2 here. I'm not going to go into depth about where this normalization factor comes from. Efrat talked to you about this. I'm not sure if she told you where.
Yeah.
Okay. So.
N plus 1. It's the factor n plus 1, 1/2, the power of 1/2.
Yeah. Yes. Good. Then good that she talked to you because I'm. And now, if I want to add a photon in a different position, let's say AI plus 1 dagger. So did I say plus 1? Plus 1. Okay. So it's like this. It's very simple. The full equation, the general equation for creation operator was taken n equal square root n plus 1 n plus 1. This is the most general form of the creation operator. Now the annihilation operator. I'll do it here. And I'll do it a bit shorter because it's almost the same. Alright, now A without a dagger. Let's take this state again without square root of 2, just simplicity. If I want to use the annihilation operator, place I, this will equal square root of 2. Again, there's some normalization factor here, I'm sure if I talk to you about. And in general, before general, I think I don't need to write it down, but if I add an annihilation operator for AI plus 1, all it will do is remove, change it to 0 and nothing else will happen. And the general annihilation operator equal square root of n minus 1. We see a few. We can already see a few things by just looking at these two operators straight. First of all, they're not really symmetrical. Doing A dagger A doesn't equal doing AA dagger, because here we have n plus 1. This is the normalization factor that corresponds to output state. And this has only a square root of n, which is corresponding to the input state. So it's a bit different. And we see that A0, A on the vacuum, the annihilation on the vacuum will give us 0. The number 0, not 0 particles and stuff like that, really the number 0. Nothing will do that. The second, third, depending on how you count what I said, a very important thing that we can see is by combining A and A dagger, we can physically get a count out of our state. What do I mean by that? If you write A dagger A on the state n, we'll get A dagger square root of n minus 1. Right? Numbers, I can move to the side. So I get the square root of n, square root of n minus 1 plus 1, and state. So we have a very nice way to write the number operator. Right. So, we got a representation, got a little bit of math. Now we only have one more thing to go over, and then that's it. You already know second quantization, you can go home and finish the course. That's how simple it is in theory. I'm going to erase this. Bye-bye. Okay, I said, when I talked about the quantum state, I said many worlds, particles, photons, electrons, stuff like that. In reality, you only need to care about two terms, bosons and fermions. All right. Bosons follow what we learn in the first half of the tutorial, which basically in 1 and 2 equal I if you don't believe me, try to open this up and see that you'll go back. Again, doing it one will create times square root of 1, do it in the second time square root of 2, and so on and so forth. You can trust me. Which is exactly what we saw. And another interesting fact about bosons, they have special relation with the creation and annihilation operator via commutation relation. I forgot the word for a second. AI AJ dagger equals for if there's a case where someone doesn't know this notation, just mean AI AJ dagger minus AJ dagger AI. With commutation A times B minus B times A, and it will be equal to delta IJ. In addition, there's also this two that we should write. Commutation relation with annihilation or commutation relation with creation itself will always be 0, even if I equals G. This is bosons. I know you're very excited. It's a lot of material. I hope you keep up. Now, unless someone has a question, let's do a little exercise using this extensive knowledge. Any questions? No? Let's say we have some state. I'm going to write it here. Phi equals 2, 0, 1. Right? And I want to know AI phi equals 2. So again, I equals 1, 2, and 3. And I want to do this only using commutation relation and annihilation on the vacuum. These two and 1. So, what do? Anyone wants to try? I know it's not very complicated. You don't need to feel scared.
You bring it to the vacuum. Firstly, you bring it to the vacuum state using an annihilation operator, and then you can do whatever you want.
Right. Before I do that, I'll say something very small. A lot of people write the operators with a hat to signify the operators. I usually remove the hats when it's obvious that it's an operator. For the same reason we write everything like this, I like to make things as short as possible. So if I write a hat, if I don't write a hat, I bet you'll be fine. You seem very smart indeed. So yes, first of all, if you want to use the commutation relation, we can't work with numbers inside the state, because how do you move it around? We need to remove the creation operator outside. So, you can check me on this. One over square root of 2, A1 dagger, A1 dagger. Note I could have wrote A1 dagger squared. I just prefer to write it like that for now. A3 dagger. Now, to do this equation, I'll just write at the AI here. Let's do one for example, and the rest you'll do yourself if you really want to. Let's start with annihilating A1. So, I want to flip, because my objective now is to move the annihilation operator all the way to the right to get to operate it on the vacuum state. So, flipping them once, we know that A1 dagger equals to 1 plus A1 dagger A1. Right? So this one will be 1 over square root of 2. 1, so these two go out, so A1 dagger, A3 dagger, 0, plus, I'm going to get the square root of 2 on the outside. Right, then I'm going to flip them again. 1 over square root of 2. 2, A1 dagger, A3 dagger, plus A1 dagger, A1 dagger, A1, A3 dagger, 0, write 0 on the outside. So on the outside. And then again, I can flip these two, except this time there won't be a 1, because they don't commute. A1 and A3 dagger don't commute using. So I have 1 over square root of 2, 2 A1 dagger, 3 dagger, plus A1 dagger, A1 dagger, A3 dagger, 1, 0. I hope you'll see it in the recording. But A1, the annihilation operator on vacuum, 0. This cuts out. Then we can take in A3 and A1. Just be equal to square root of 2, 1, 0, 1. Which we expected based on this equation right here. Alright, this is boson. Amazing. This is bosons. Do you want me to do A2 and A3? I think we have time, but I don't think it really add much. Alright, so now bosons' stranger cousins, fermions. I forgot to reset something. Fermions are special. They like to think themselves unique, so you can't have two fermions that you can distinguish between. It's called the Pauli exclusion principle. I'm sorry, I'm bad with names. Pauli exclusion principle says that you can't have two electrons that you can't distinguish between them. So instead of what we wrote for the very general boson state, fermion state, you read it as where there's a few like stars on this equation, where Ni is 0, 1, and I'll start the counting of this to multiplication from infinity to 0 to 1. It's fine. It's 0. I'm going to start from infinity to 1 here. We'll see why is that in the soon up and coming exercise. We'll just keep that in mind. And they also, again, like to be very, very unique. So they go with the anti-commutator relation, which we denote with curly brackets. AI AJ dagger equals AI AJ dagger plus AJ dagger AI delta IJ. It's exactly the same as boson, but they have to be special, so they have a plus here. The second part is exactly like boson, but with anti-commutator. Now let's do a very similar question, but with fermions. Again, fermions can't have 2, so I'm just going to replace this with 1. The rest of the question will be this. So, let's do it again. Same question. This time I'll do A1 and A3. I'll do them both. And let's do prep AI phi. Again, we move the particles from inside the way the inside of the quantum state to the outside. Let's already start A1. A1 dagger. Note that I start from the end. 0. Again, I'll switch between them. So A1, A1 dagger equal to 1 minus A1 dagger A1 equals to E3 dagger minus A1 dagger A1 3 0 A3 dagger. Now note again, A1 and A3 commute freely. There's no 1 here, but there's another minus come from here. Again, because here there's a plus. So this will be equal to E3 dagger plus A1 dagger 1 0. Again, annihilation operator on the vacuum is 0, just be 0 0 1. Now let's do A3. What can I write? I want to write it here. A3 of phi equals A3, A1 dagger, A3 dagger, 0. Again, switching between them to the minus, A1 dagger, A3 dagger, 0. And again, switching between them. This will be minus A1 dagger plus A1 dagger, A3 dagger, A3, 0. This one gets removed. Then we get minus 1 0 0. Weird. Why is there a minus? Well, why there's a minus there? It's not really important. It's about it's about convention of writing. The minus could be if we counted all the photons in the other direction. For example, if we reorder this as first we take photon number particle number 3 and then particle number 2 and then particle number 1, we'll get minus in this equation. So where the minus comes from doesn't really, or when it lands doesn't really matter. It's important that you stay consistent, again, with everything. As long as you stay consistent, this minus won't give you any trouble. But to stay consistent, let's expand this this definition here a little bit to say AI dagger of N1, N2, and I infinity equals, let's say we have a 0 in I, equal to minus 1 to the power of sum over j. J is from 1 to I minus 1, and 1 into 1I. Basically, we count all the particles before the location that you want to put something in or take something out, and multiply it by an minus 1 to the power of this sum. Can you see? It's a little bit crowded here. Can you see it? You need to write it again. It's fine. Good. We actually,
That's like the exercise you did, the example. You will never do that, right? You will just calculate it.
Here, yes.
It's just
In this form, yes. But we'll learn during the course that there's usually two main way to solve problems in second quantization. One of them is called the Schrödinger representation, where we take a state, this one, and advance it through time. And advance it through time. And then there is what we call the Heisenberg representation, where we work with a vacuum state, transfer all of our information to the operators, then move the operators through times. So sometimes we'll solve problems.
Assuming that you start with the vacuum state.
But I can move everything outside. Can I move everything outside, or I can? You'll see when we talk about it that we can also do transformation on the operators that represent advancements in time. So these two different representations are very important. So since we're ahead a little bit, we'll do one more example, and then we'll take a short break, and we'll see an actual application of what we sorted right now. So let's do one exercise, then take a short, like 10-minute break. All right. Let's consider two-level fermionic system with some number lambda, which again is lambda 1, lambda 2. And I want to find the matrix representation of A1 dagger. Okay. So this, by the way, this question might look super simple. It is very simple, but it will come back in the future. Probably in your future, if you're working quantum, something very similar to this will come back. So the first thing that we need to do to find the matrix representation is to find a basis. I think this is the easiest start, and we'll just take the trivial basis. I hope I have enough markers this time. 0, E2, 0, 1, E3 equals 1, 0. I wish I wrote it a little bit to the left. Right. Now, to find all the elements on the matrix, we simply need to do another bad one, go on exile. Simply need to do A1 value EJ. So D A1 value. Simple, equation. Now, before we start, we already have a few terms that we can remove. First of all, E3 and E4 operating the equation operator on 1, either of those will give 0. So all the columns 3 and 4 will be 0. Second, so let's see what E1 and E2 with A1 dagger will give us. So A1 dagger E1 equal to A1 dagger 0, 0 equal to 1, 0. A1 dagger E2, A1 dagger 0, 1 give us 1, 1. We know this is E3 and this is E4. So the only non-zero elements, since all of these are orthonormal, the Fock state are orthonormal. If I don't remember if I mentioned it when we talk about Fock state. The Fock state are orthonormal. So only E3 A1 dagger E1 and E4 A1 dagger E2. This will be the only non-zero terms, which will give us A1 dagger equal to 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. Short and quick. Let's take a 10-minute break. Come at 10 minutes to before 7. And we'll do Schwinger bosons. Yes. Schwinger? Don't catch me on the pronunciation, but I'm pretty sure it's Schwinger bosons. Okay. Maybe. I don't know. מישהו פה יודע על ההקלטה, עשיתי כבר. הגעתי עם משהו ואני מפסל לו.
יש איזה כפתור כזה שמחליף בין ה...
לחצתי על אחד מהאפי, ואני לא רוצה ללחוץ על אחד ברצף. אני כרגע בדוק איזה טוש טוב. אנשים לא רוצים להכין דברים עם הידיים. האם זה לא שווינגר? זה לא שווינגר?
בדקתי את זה, הוא אומר שווינגר, צודקת.
זה לא מעניין מתרגם. Okay. So, we talked about getting representing a large sum of particles or forms or whatever in a very simple way. But here, I want to take one particle, which is a little bit complicated, and represent it by a many particle system, which is a bit simple. What do I mean by that? Let's say I have some particle and a spin. We can represent it using S. S, the total spin number, M, the positive spin value, where we can notate this, where S again is the total spin, M is Z oh goodness. Z component right, and actually you don't need the absolute value here. This is a positive number. And we know that we can, let's say some stuff that we know about the system. We know that we can change M, this one, by the S plus operator, and we can change M minus 1, S minus operator. Again, we have the SZ operator, and so on and so forth. You'll see some more operators in your homework. Okay? Now, let me start by drawing some. I want to draw all the possible states that I can find this particle. I'm even going to put nice little arrow. No! How can I have so many markers? It's still bad. Is it something about me? Alright.
Maybe it's the bold.
Maybe. General SM could be this one. Sorry. 1 minus S. And minus S. This is every single particle. And I want to equivalent it to some ensemble of different particles. How am I going to do it? Well, let's say that we have a positive particle, A, for example, and a negative set of particle, B. And when I move from a different Z spin component levels, I move a particle from positive to negative, or vice versa, right? So basically, what I want to say is, let's say I have box A, box B, and moving down this ladder will just take a particle from A and move it to B. This will be the equivalent. So for that, I'm gonna take a bigger box. No. And say first of all, n equals 2s. Why 2s? Because a transition one side to the other will give us a difference of 2 between them, each transition. And I would like to say that
Hello, 2s plus 1.
not 2s. You'll see it. No, it's 2s. I would like to say NA minus NB equal to N, A plus B to S. Why would I like to say that? Because I can very simply equivalent say I can very simply extract from Fock state, a new Fock state, the quantities from our original spin state. Okay. So, if for every S and M, we'll take state that is equal to S plus M, S minus M, or get this very simple. I will get exactly what I wanted very simple. Or, if you want this with operators, will be A dagger S plus M, B dagger S minus M, by the square root S plus M dagger, by the square root S minus M, another power. Note that you might see here a simpler way where we don't need the 2 here, and we don't have S plus S minus. But have the S plus S minus. I'm not exactly. I didn't read Schwinger's paper, so I don't know his reasoning for building it like this. But I see it as avoiding negative and complex state, and this is very simple. And give us all the information directly from the particle counts. So how would this look? You know, I gave us a very clear diagram for the spin state. How would this particle state look? Let's again write it here in the side, the spin state, and just so we have it in the contrast. S minus 1, S 1 minus S. Right. So for the 2-particle system, I will write a table with the number of particles in A or the number of particles in B. Okay. So S, we can just, very bad choice of word, but okay. The first one, we can see that M is equal to S, it's always equal to S. So we'll have 2S and 0. The next one, S plus S minus 1 will be 2S minus 1, and S minus 1 will just be 1. So forth and so on and so forth. 2S minus 1, S 1, 0. Now, even before we start analyzing the 2 systems or that stuff, we can see a few simple things. You can see that reducing the spin component, the spin Z component by 1 would mean this transition will be very simply written as A B dagger. The opposite transition will be E dagger B. Right, so this is a very simple solution. Now let's try to look at some properties of this transformation and see if it's actually valid. Try to prove that. Start to prove that it's actually valid. Some of it you'll do at home, some of this we'll do right now, and we all have a good time solving some quantum questions, some physics questions. All right. So a good way to prove that this transformation is consistent is basically check everything that we know about spin states and stuff like that. For example, we can check the spin operator squared of Sm should be equals S plus 1 Sm Sz Sm equal n Sm, and of course we also need to find these operators. Luckily for me, especially for me, those two are in your homework. Congratulations. Although we'll see the operator Sz here. So what we'll do in class is we'll try to find the representation of S minus, S plus, which of course we already saw by simply drawing our two systems and seeing the connection logically. And we'll find Sz, and then we'll see. Okay. So question of class A. Right. S plus, S minus. Single boson. Well, since we don't have the, I didn't make a full mathematical transformation. I just built it as I went along using logic. We already extracted it, even though we don't really have the math connection between these two systems. But using these two, we can create an entire full transformation for all the operators, so on and so forth. So again, as we saw here before, we already wrote this S plus. I will never have a good marker there. B S minus equals B dagger A. Right? Two things to note here. Two things. Right? First of all, we know S plus equals to S minus dagger. This is from, you should have seen this previous quantum courses. And we see it. We in fact see it here. The dagger moves places, and even though they commute and we can write A, B dagger or B dagger A, I chose to write it like that, first of all, because I put the dagger on the left, which is very useful. Second of all, operators are almost matrices, pretty much matrices. So when you do a conjugate to a multiplication of matrices, also rotate. So when we take this equals to, oh no, you both switch the order and put a dagger on everything. So again, B dagger B. Luckily for me, I came prepared. Let's say you want the blue color. Blue color, so I think it's good. Let's try this. Okay. So pretty simple. Next, B. Find Sz. Right. First of all, we can do the what we did before, the very simple. Look at this very informative graph and say in Scotch or Chin and find this. Or we can do the fun thing, which is probably a little bit longer, and try to use known connections, connection between the different operator in the spin space. Because if the transformation is valid, the connection should still remain. So what's the connection? The connection in the spin notation is S plus S plus S minus equals to 2S. Alright, I'll continue here. Okay. So S plus will be A dot B, B dot A. Let's write it out. I'm going to use, instead of fully writing it out, which we can, I'm going to use an identity. It's the first identity of the course. The identity will be A dagger BA plus. I'm going to write what it equals to. The identity itself, like the general form, would be is in the tutorial notes. So I'm not going to write it again on the board. It's a waste of your time more than mine. A dagger, B dagger, A plus B dagger, A, B plus A dagger, B dagger, B. Right. First of all, do the commutation relation. The first and last term cancels out. This one, U1. This one, -1. So this is equal to A dagger A minus B dagger B. Therefore, SZ equals to A dagger A minus B dagger B, square root of 2. Okay, not square root, just divided by 2. This, of course, matches how we built this transformation in the first place. We said the Z component will be the difference between the two particle numbers divided by 2. And we saw in the first half of the tutorial that A dagger A is just equal to A. So all of this makes sense, and we see that they're very consistent, and very good and happy, and all of this stuff. Any questions before we move to C? Any questions? Any questions? Just a little bit ahead of time, so we got time if you want to ask anything. All right.
Like we are just given the identity that FB equals the commutation that you would just.
Yeah, the commutation between plus and minus equal to SZ. It's an identity that you're supposed to know from
back then.
Yeah. You'll see this excuse a lot in the upcoming degree. You should know this. How should you know this? You should know this. Okay, so last part, we want to check another thing for consistency. We want to check, let's see, Z plus minus equals plus minus. And this is just a test for consistency. So let's open this up. This will be a dagger a minus 1/2 a dagger a b dagger b. Let's start with the plus, for example, a b dagger. So, first of all, second identity, a plus b equals a c plus b c equals 1/2 a dagger a dagger b minus b dagger b a dagger b. I actually used another identity twice. I'm gonna write down here. And if n is a number, it's like a trivial identity, but I shouldn't write it. Right. Now again, these two I can open with the same identity that I used here and get a very, very long one. That's good. This will take 1.5. A dagger b plus a dagger b a plus a dagger a b minus b dagger a dagger b b minus b dagger b a dagger b minus a dagger b dagger b b minus b dagger a dagger b b. Now, this one cancels out, this one cancels out, this one cancels out. Again, all of this from commutation relation. This one cancels out, this one cancels out, this one cancels out. So we have 1/2 a dagger b. This one equal to 1. Remember, if the creation operator is on the right, it's equal to 1. If it's on the left, it's equal to -1. So plus a dagger b equals a dagger b, which equals to s plus. Okay, we can do the s minus, but trust me, it will look exactly the same. So I'll excuse you from this, from the s minus 1, and ask you, how far did you get with the one body operator with Efrat? So she just started.
You just mentioned that.
Okay, so the next subject will be one body operator, but since she just talked about one body operator, we won't do it right now. So yeah, this example didn't have a lot of like deep substance for discussion inside of it. It just meant to show you how we can take a complex system and try to represent it simply with second quantization. Now, when I say simply, when I claim it's simpler, it's much easier to work, this is my opinion, it's much easier to work with creation and annihilation operator compared to the many spins operators. So it's a very useful transformation. And any questions about the Schwinger boson? You will explore this system a little bit more in depth in your homework. So I have a little say. If you don't have any questions, this is basically the end of this tutorial. The first one, but it was a good one. It was the basis. And yeah, now you know the entirety of second quantization. Basically, you know the entirety of second quantization. You just the rest of the course is just learning tricks and
so basically
uses and stuff.
Second quantization is taking stuff and operators and making them into ladder operators.
Yeah, second quantization.
Effectively speaking.
Second quantization basically comes from the idea that it's very simple to take known stuff and put them into box, and then basically 2 + 1 on the box, -1 on the box, and build more complex system using just ladder operation. And we'll see that we can use ladder operation to even represent very complex system like squeezing, superconductivity, and so on and so forth. But the basis of everything we will see will just be this.
אז זה גם אומר אבל שאתה צריך, זה אומר גם שאתה צריך להסתכל להגדיר את המצבים שלך בטוב, ברמה כאילו הניסיונית, לצורך, אם אני רוצה להגדיר את התקופה שלי, שאני מעביר בינה לבין...
Yes, there is, that's a good point, and if we'll, I'm trying to think of an answer for now, because this question will probably come up also later in the course, because we will talk about grand canonical systems, like system, for example, a laser, you know, you don't have a, okay, let's start with something, Fock state, 1. How many, let's say I'm talking about photons because I want to compare to lasers. How many photons do I have?
אוקיי, אתה לא באמת יכול להגיד לך אתה לא באמת יודע שיש לך אחד.
In a Fock state, yes, you have 1. There's a problem generating Fock states, but that's something completely different. Laser, alpha, maybe alpha equals 1, it says that you have an average of 1 photon, but again, you don't really know how many photons. למה אני מדבר באנגלית?
גם אני התחלתי.
אתה לא באמת יודע שיש לך פה 1 פוטונים בלייזר, אתה יודע שיש לך ממוצע, שמצב מסובך גן קנוני כזה שיכול, ואתה יכול עדיין להציג אותו עם פוקס שייט ואתה מגיע לזה.
גם המספר המדויק, אני לא מדבר כמו על המספר המדויק, אני מדבר שאתה צריך להגדיר את המצב בעצמו. עם לייזרים זה יחסית פשוט.
שים לב שבקונדנסט שנייה אנחנו מדלגים על להגיד את המצב עצמו. אין לי יותר פונקציה לגל, באמת. אני אומר, יש לי פוטון אחד באנרגיה 3.
אבל אני אומר, אתה צריך להגדיר, פשוט, לצורך העניין, יש לו מערכת סופר מוליכה או משהו, יש לו כל מיני סוגים של מצבים שיכול לנוע, והוא יכול לנוע ביניהם. אוקיי? עכשיו, אני אומר, אני צריך לדעת אפריורית מה המצבים האלה. אז או שאני עכשיו הולך לבדוק מלא, לא יודע, להעביר בו מלא מתחים, טמפרטורות, whatever, או שאני יודע כבר מראש את הסימטריה שלו ושתוכל לבנות עם מילטוניאן ולנחש מה המצבים שלי.
על הרוב, שאתה עובד בקונדנסציה שנייה, בדרך כלל מתחילים עם המילטוניאן. אתה בונה מילטוניאן מניסוי העבר עם כל מיני בדיקות כאלה, מתיאוריה, ואז בתוך המילטוניאן אתה יכול למצוא את המצבים העצמיים, איך הוא מפתח נגיד ואקום עם הזמן, דברים כאלה, זה ממש שימושיים, ואז לפי זה אתה יכול ללמוד קדימה. שעוד פעם, אתה מדלג על הרבה שלבים באמצע של לבנות פונקציות גל באמת וכאלה. ובנוסף, אנחנו לא ממש ראינו את זה פה, אבל עוד מעט נדבר על ארכיטקט ספית, שאז אתה יכול באמת לשים לך דברים, לדעת מה אתה יכול למדוד וככה לעשות פרדיקציות, שלפי זה אתה בודק מודלים. אבל בעקרון ככה זה כל פיזיקה, אתה מנחש משהו לפי מה שאתה רואה, ואז אתה בודק אם זה נכון בהמשך. קוונטים, יש לו את הסיבוך שיש תמיד לקוונטים, שזה הכל סטטיסטי. עדיין צריך לנהוג פה?
אני לא יודע. נראה לי שדלתורה דיבר על זה בקורס שלו, על לייזרים.
על מה?
על בדיוק על העניין הזה, ספציפית עם לייזרים, הוא דיבר על פוק סטייטס, כאילו... וגם שם שאלתי אותו, והוא אמר, בלייזר זה קל, אתה יודע מה המצבים האפשריים של הלייזר, התיאוריה על לייזרים ממש ידועה טוב.
כן, יש מצבים ממש מסובכים, נגיד שאנחנו נלמד, שאני אומר שאנחנו נלמד מוליכי